Hi folks, Dr. P here. This is question number 15 from the probability assignment. The table shows the distribution of blood types for students in first year at the local college. And in A, they want us to complete the totals in the chart. So it's just a matter of adding up the rows here to get a total. So for example here, the total number of males are 500 if we add up these four numbers. So we're going to get 500. The total number of females are 750. And then we're going to add up the columns. So these are the blood types. So the total number of individuals with blood type O is 525. The total number of individuals with blood type A is 435. The total number of individuals with blood type B is 185. And the total number of individuals with blood type AB is 105. And then in this corner cell, we're going to have the total number of individuals, which we can either get by adding up these four numbers or the number of males and females. Either way, we're going to get 1,250 individuals. All right. In B, they're asking us how many students are in first year college. Well, that's this number right here. So it's 1,250 students. In C, use the numbers in the table to determine in simplest fraction form the following probabilities. Okay. So the first probability is the probability of having blood type O. And remember, when we calculate the probability, it is number of favorable outcomes in the numerator divided by total number of outcomes. So in this case here, the number of individuals with blood type O, that's our number of favorable outcomes, is 525. Divided by the total number of individuals, which is 1,250. Okay. They want us to leave it in fractional form, but we have to simplify. So in this case here, we can reduce this to 21 over 50. And that's in simplest fractional form. In the second question here, they're asking us for the probability of blood type B given that it's a female or females. Okay. So the way we're going to go about calculating this is we're going to use the formula for the probability of two events occurring at the same time, which is probability of event, in this case event B, so having blood type B and blood type F, is equal to the probability of blood type F times the probability of blood type B given that it's a female. Okay, so this is the formula for dependent events. Okay, the two events depend on each other. Now, in order to calculate this, we're going to need to break this down a little bit. So actually, I'm going to move over to the side here. I have more space. I'm just going to write I there. I'm going to write this down here. So probability of blood type B and blood type F equals the probability of, sorry, not blood type F, female. The probability of a female times the probability of having a blood type B given that it's a female. Okay, so that's the formula we're going to be using here. So what we're looking for here is this. And what we will do is we're going to determine the probability of B and F, and we're going to determine the probability of there being a female or a female being selected. If we know these two quantities, we can then solve for the probability of B given F. Okay, but the first challenge here is going to find these two quantities. So let's start with the probability of blood type B and being female. Okay, This is equal to the probability of blood type B times the probability of it being a female. And now we can actually plug in these probabilities using our table here, right? So what's the probability of blood type B? Well, the total number of blood type Bs were 185. And the total number of the total number of individuals was 1,250 times the number of females in this study was 750 divided by the total number of individuals, which is 1,250. Okay. Now we can reduce this a little bit. So before we do the multiplication, if we do the multiplication with these two quotients, we're going to end up with very large numbers. So 1,250 times 1,250. Trying to reduce that's going to be difficult. So this quotient here, 185 divided by 1,250, can be reduced. Let me just grab my calculator here. It can be reduced to, I just have to quickly double check. Yeah, if we divide numerator and denominator by 5. So 185 divided by 5 is 37. 1,250 divided by 5 is 250. Now 37 is a prime number, which means that we cannot reduce this any further. And the second quotient here, we can reduce that by dividing numerator and denominator by 250. So 750 divided by 250 is 3. 1,250 divided by 250 is 5. Okay, so that's a little bit more manageable. If we do that multiplication, we're going to get 111 over 1,250. All right, so this is the probability of blood type B and being a female. Okay, so now we need to find the probability of being a female. So we already have that, actually, it's right there, but I'm just going to write it out like this. Probability of a female is 3 over 5. It's this one right here, right? So now we can plug it in. So we can plug it into this formula right here. So on the left-hand side, we're going to have the probability of blood type B and female. So it's 111 over 1,250. That's your left-hand side. Okay, equals to the probability of female 3 over 5 times the probability of blood type B given female. Okay, so now we can solve this for this probability. We simply divide both sides, we multiply both sides by the reciprocal of 3 over 5. So that's sort of a little trick. If you want to get rid of a fraction when we're solving an algebraic expression like this, we just have to multiply both sides by the reciprocal of that fraction. The reciprocal of a fraction is just a fraction sort of reversed, upside down. Okay, so if we do that, we're going to be left with the probability of blood type B given female equals 111 over 1,250 times, and then the reciprocal of this, which is 5 over 3. Okay, and again, just like before, we can actually reduce this at this point. So here, for example, we can divide 5, we can reduce 5 and 1,250, divide both by 5, which leaves us here with 1, and 1,250 divided by 5 is 250. We can divide 3 by 3, which leaves us with 1. 111 divided by 3 is 37. So what we've done here, we have simplified these fractions diagonally like this, and you can do that when you multiply quotients. All right, so now we can do that multiplication. And because we already simplified, it's going to be a little bit easier. The numbers are going to be smaller. So 37 times 1 is 37. 250 times 1 is 250. Okay, so this is the probability of blood type B given that it's a female. The trick here is to always reduce these quotients as soon as you can. Okay, so the first example here was up here. We were multiplying these two quotients, but instead of going ahead and doing that, we reduced this and simplified it to this expression right here, right? Which resulted in much more manageable numbers. You can certainly multiply 185 times 750 and 1250 times 1250 and then reduce, but you're dealing with much larger numbers and it'll be substantially harder to reduce that quotient. Same thing over here. Okay, so always reduce fractions as you go along. It's better to do that than wait to the end, particularly in this example here. Okay, so that was question 3, this one right here. Now we have question 4. So I'm going to see if I can fit that a little bit on the side. Okay, so we want to determine the probability of female and blood type B. Now it turns out that well, we're going to use the same formula here. So actually what we're going to do here is we don't even have to use the same formula. We can do this. This is much easier. So since we've done all of these calculations, we can take advantage of what we have here. So what's important here is that the probability of female and blood type B is going to be the same as the probability of blood type B and female. So if you think of this in terms of set theory, this is essentially set theory notation where we're looking at the intersection, the overlap between, in this case, these two sets, F and B, females and blood type B. So it doesn't matter which way you write it, it's going to be the same, right? So in this case, this is useful because we already know the probability of blood type B and female. We have it right over, where is it? Right there, right? So in this case, it's going to be the same number here. Let me just move it over here. So it's going to be the same number. So it's going to be 111 over 1,250. That's the probability in simplest fractional form. Okay. So that is, was that question 4? Yeah, that was question 4. That's it. Okay, so we did all those calculations in question 2, and then that simplified our life in question 4. Okay, so let's move on. So in question D, if a student is selected at random, determine the probability to 4 decimal places. So now we're dealing with decimals here. So to 4 decimal places, that a student is male. Okay, so this is fairly straightforward. We already calculated probability of a student being a female. It's exactly the same procedure, except that this time the probability of male is going to be the number of males in the numerator. We have 500 males divided by the total number of students, 1,250. And we can reduce this. Well, we could reduce this. We don't necessarily have to reduce it. We can just divide because they actually want this in decimal form with 4 decimals. And if we divide this, it's going to be 0.4000. So they want 4 decimal places. Those 3 trailing zeros are important here. Okay. In question 2 here has blood type A, so probability of blood type A. So same sort of procedure, so number of favorable outcomes. So the number of individuals with blood type A is 435. And the total number of individuals again is 1,250. And if we divide those numbers and provide our answer to 4 decimals, it's going to be 0.3480. Okay, and then question 3. So the probability that a student is male and has blood type A. So and means intersection, right? So probability of male and blood type A. Okay. So, well, now we can use these two probabilities as we have here. So the probability, so we simply have to multiply the probability of a student being male times the probability of having blood type A. These are independent events, right? So both of them can happen at the same time. A student can be male and have blood type A, right? So it's just a simple multiplication. So this is going to be 0.4000 times 0.3480. And that's going to be 0.1392. All right? Okay, so that's sort of the first half of this question. Let's move on to the rest of the question. E. And so in E, they're asking, are the events, the student is male and the student is blood type A, independent events? Well, I just actually mentioned that. Yes, they are independent events. So yes. Why? Because both of these events can happen at the same time. Okay, so they are independent events. All right, so in F, so identify the following events and determine the probability as exact decimals that a female student has blood type A. Okay, so what we're looking for here is the probability. This is 1, yeah, F1, I guess, yeah. So a female student has blood type A. So we're looking for the probability of blood type A given that we have a female student. Okay, so this is what we're looking for. So again, we're going to be using the formula for dependent events. So it's going to be the probability of a student being female and having blood type A equals the probability of a student being female, which we already know, we calculated it earlier, times the probability of a student having blood type A given that the student is female. Okay, so this is the formula we're going to be using. So the probability of a student, so first we have to determine some quantities. We have to determine this. We know what the probability of female is, and this is what we're looking for. Find this. Okay. So the probability of a student being female and having blood type A is simply the probability of a student being female times the probability of having blood type A. We know that the probability of a student being female is 3/5. We calculated that earlier on, right? And the probability of student having blood type A, I don't remember if we calculated that. If we go back, yeah, it's right there, right? So it's 435 over 1250. Or we can use the decimal form too, I guess, 0.3480. 0.3480, right? 480. So we can use the decimal form because they want to answer in as decimals, right? So if we multiply these two numbers, we're going to get 0.2088. So that's the probability of a student being female and having blood type A. Okay. So now if we look at this expression here, we know this probability, we know this probability, so now we can solve it for the probability of blood type A given female. Okay. So we just plug in the numbers that we have. So 0.2088, that's your left hand side. The probability of a student being female is 3/5. We can actually convert that to decimal form since we're working in decimals here. So it's going to be 0.6 times the probability of blood type A given female. Now we just solve it for this. So we're going to get the probability of a student having blood type A and being female, given female, is going to be 0.2088 divided by 0.6. All right, and if we do those calculations, divide those two numbers, we're going to get 0.398. Okay. So that's number one. Number two here. Identify the following events and determine the probability that a female student does not have blood type O. Okay. So the way we're going to represent this is we're going to use the complement to O. So this means not having the blood type O. If we go back to our table up here, the table shows us the number of students that have blood type O is 525. The number of students that do not have blood type O, well, it's going to be, if we add up these three numbers. So this here is going to be the number of elements in the complement to O. Okay, so this is set notation. If we add up these numbers, we're going to get 725. So there are 725 students that do not have blood type O. Okay, so we're going to use that here. Where was it? Oh, we haven't started yet. So question number 2. So a female student does not have blood type O. So question number 2. Okay. So what we're looking for here is the probability of having blood type, not having blood type O prime, right? The complement of O, given that it's a female student. And again, we're going to be using the, where is it? The following expression, right? The same formula, but we're going to change some of those letters in there. So it's going to be the probability, so this is what we're looking for, the probability of not having blood type O and being female equals the probability of being female times the probability of not having blood type O given that student is female. Okay, so again, just like before, we're looking for this. We need to know the probability of being of a student being female, which we know. We have it up here, 3/5 or 0.6. And then we also need to know the probability of a student not being female, not being blood type O and being female. This is simply the probability of not having blood type O times the probability of being female. So the probability of not having blood type O, we said there were, what was it, 725 students that did not have blood type O. So 725 divided by the total number of students, 1,250, times the probability of a student being female, which is 3/5. Okay. Now we can reduce here, so let's do that. Okay, so this quotient right here can be reduced just so we work with a little bit smaller numbers. The numerator and denominator can be divided by 25, right? And if we do that, 725 divided by 25 is 29. 1,250 divided by 25 is 50. Okay, so it just makes the numbers a little bit more manageable. So what we're left with here is 29/50 times 3/5. Okay, and they want it as, we're going to express our answer as a decimal. So in this case, if we evaluate this, we're going to get 0.348. Okay, so that's the probability of not having blood type O and being female. So now we can go back here, we can plug in these two quantities that we now have and then solve for the probability of not having blood type O and student being female. So it's going to be 0.348 on the left hand side. Probability of being a female is 0.6 times probability of not having blood type O given that it's a female. So this is probability just divide both sides by 0.6, right? Probability of not having blood type O given female equals 0.348 divided by 0.6, which is 0.58. That's your answer. And I don't think they said anything about decimals, did they? Exact decimals, so that's it. Okay. All right, so there is question 3 as well. In question 3, we want to determine the probability that a student with blood type blood type A is male. Okay, so I'm going to move sideways here because we need more space. So this is question 3. So what we're looking for here is the probability of a student being male given that he has blood type A. That's what we're looking for. And again, we're going to use exactly the same procedure. So we're going to be using the same formula here. So the probability of a student being male and having blood type A equals the probability of the student being having blood type A times the probability of the student being male given that he has the blood type A. And here we're looking for this. Okay. So again, we need to know these two quantities, which I don't think we have calculated yet. So let's just start to finding the probability of a student being male. So we go back to our table there, and I believe there were 500 male, so it's going to be 500 divided by the total number of students, 1,250. And we're dealing with decimals, so let's just turn this directly into decimals. The probability is going to be 0.4. So this makes sense. Remember how the probability of a student being female is 0.6? Well, when you pick a student, it's going to be either a male or a female. So a student being male is the complement to a student being female. So the two probabilities have to add to 1. 0.4 plus 0.6 is 1, right? So this makes sense. So it's a quick check to make sure that we're on that we didn't do a mistake here. What did I just calculate? Probability A, blood type A. I think I just did the wrong thing here, didn't I? I did. Hold on. I can fix this quickly here. Shouldn't say A. We calculated the probability of a student being male, right? Okay. It's a long question. Yeah, it should be M. The probability of a student being male is 0.4. Now we need to find a probability of a student being or having blood type A as well. Okay. The total number of students that had blood type A is 435. The total number of students is 1,250. Divide those numbers and we're going to get 0.3480. Okay. And now we can go ahead and calculate the probability of the left-hand side here, the probability of a student being male and having blood type A. It's simply going to be the product of the probability of a student being male times the probability of a student having blood type A, which is 0.4 times 0.3480. So this is 0.1392. Okay. And at this point, we can proceed and plug in what we know. We know this and we know this, and then we are looking for the probability of a student being male given that he has blood type A. So it's going to be 0.1392 on the left-hand side. Probability of having blood type A was 0.3480 times the probability of a student being male given that he has blood type A. Divide both sides by 0.3480. And we're going to get the following expression. Okay. If we evaluate that, we're going to get 0.4. Okay. And then there is one more question here. Go back here. So under F, there's one more. The probability that a student with blood type AB is female. So it's going to be very much the same exercise. So I will do that one here as well. So this is question 4, right? So question 4. So what we're looking for here is the probability that a student is female given that she has blood type AB. And again, we're going to start with the same formula as before. So the probability of a student being female and having blood type AB equals the probability of the student having blood type AB times the probability of the student being female given that she has blood type AB. All right, so this here is what we're looking for. Okay. So we don't know what the probability of AB having blood type AB is yet. We just have to calculate that. So probability of having blood type AB. So we just have to go back to our table and find those numbers. So we have 105 people with blood type AB, and the total number is 1,250 individuals. And if we divide those numbers, we're going to get 0.084. Okay. Then we have to find the probability of female and blood type AB. Female and blood type AB, which is simply going to be the probability of a student being female times the probability of having blood type AB. We know that the probability of a student being female is 0.6. Probability of a blood type AB is 0.084. Okay, and this is 0.0504. Okay, so we are ready to finish this up. We have this quantity, it's right down here. We know the probability of blood type AB is right there. So it's just a matter of plugging it in again and solving it for the unknown quantity. So it's going to be 0.0504 equals 0.084 times the probability of being a female given that you have the blood type AB. Divide both sides by 0.084. And you're going to get 0.0504 divided by 0.084. Okay, and that's going to be 0.6. Okay, so that's F. Now, did we finish F? We finished F. I think there's one more question, but it doesn't involve any calculations. Okay, so in the last question here in G, they're asking, explain why the following statement is true. So the probability a student with blood type A is male plus the probability of a student with blood type A is female equals to 1. Why is this true? Well, because these two events are complementary events. Okay. Either the first event is true or the second event is true, right? So any individual blood type A will have to be either a male or a female. There are no other options, right? So they're complementary events. They have to add to 1. But if you look at the second statement here, probability a male student has blood type A plus the probability a female student has blood type A does not equal to 1. So these are not complementary events. Not complementary events. Why? Well, because there are more than that one blood type, right? So a male student could have blood type O or B or AB. So these are not complementary events. They could not add to 1, right? So just because you know that the probability of a male student having blood type A, you cannot determine the probability a female student would have blood type A, because there are other blood types as well, right? But if you know that a student with blood type A is male, then you also know what the probability is that a student with blood type A is female. It's simply going to be 1 minus that probability, first probability. Okay? So I hope that explains it, and I hope this helps.